Okay, let me go ahead and hit go live. All right, now we're live. Okay, and we're live. So a few minutes late, but we're now up and running. So today we're going to go ahead and talk a little bit about some of the goings on that have been happening inside the Akka.NET project, starting with the Akka.NET 1.49 release, which I'm going to go ahead. Not quite done with the release notes yet. I actually have to go and type up the community contributions bit at the very end, and I think this is actually going to the wrong milestone. There we go. Fix that. Go ahead and drop a link to this on our pull request here. We're doing live coding today. How great is that? I've got Andrew and Gregorius from the Akka.NET project with me, and I've thoroughly tested all of our audio, so I know it works this time around, so that should all be well and good. All right. So the first thing I want to talk about as far as what's on our agenda is I want to go ahead and dive into Akka.NET 1.419, which is the new release that's going out today. And this covers a gigantic range of fixes for both Akka.Cluster, Akka Core, as well as there's some Akka Streams bug fixes and other stuff in here too. So let's go ahead and dive into that. Starting with the Akka.Cluster improvements. So we had one particular issue. This Akka.Cluster quarantining and reachability changes appear to be extremely sensitive. I personally spent in the ballpark of 150 hours debugging that during the month of April alone. So that's quite a bit of work for one issue. But in the course of trying to address this particular problem, we had a chance to go ahead and fix at least, I think it looks like about 10 issues here, where we went ahead and added some warnings on the fire accrual detector when heartbeats are slow. We added a new feature, which unfortunately we're not going to be able to turn on for a while because it changes the wire format of how heartbeats are done in Akka.Cluster. So probably in Akka.NET 1.5 will turn this on. But what this is doing is it's introducing the ability to log the latency between when you sent a heartbeat and when you get a reply back. So that's in there. We went ahead and we improved the performance of the heartbeat node ring in a pretty major way. So as part of trying to fix this issue, we took a look at some potential concurrency and performance problems that it might have been having, and we fixed some of those. So we made the heartbeat system a lot faster inside Akka.Cluster. We introduced a small change that makes it so when a node is joining a cluster, it will not be moved to a weekly up state unless it's been in a joining state for about 7 seconds. This is designed to reduce the number of rounds of gossip it takes for a new node to come and join a cluster. So rather than it taking 2 rounds of gossip, a node can go, well, actually, rather than it taking 3 rounds of gossip for a node to effectively transition from being a brand new node to joining to then up, now it only takes 2 in most cases here. So this kind of helps reduce the amount of work it takes to have nodes join a cluster. This is more important for bigger clusters than it is for small ones typically. We made some very big performance improvements to vector clock. As it turns out, key value pair .equals emits a ton of small objects. So if I take a look at this thread, I've got all the benchmark data on here. But if I go and I scroll down towards the bottom here, we're able to go ahead and reduce allocations by 90% and reduce the execution time of doing like 1,000 vector clock comparisons. Vector clocks are how we version the state of what the cluster looks like at any given time. That's sort of an object that helps us guarantee eventual consistency inside the cluster. But by just changing from a key value pair to a value tuple, we were able to reduce allocations by 90% and cut the execution time for 1,000 comparisons from 100 milliseconds down to about 40. So you can see the numbers in here. That's actually a pretty substantial improvement. We're going to port those vector clock changes from Akka.Cluster to distributed data as part of Akka.NET 1.420, which is the next version of Akka.NET that we have planned. This should help make distributed data a lot more memory efficient. On top of that, should also help the amount of latency it takes for 2 nodes to become consistent with each other a lot lower. So we'll be porting those same fixes we discovered here to distributed data in the next release as well. So that's something that we worked on. And then we did basically largely a lot of refactoring, and we fixed one small bug in Akka.Remote. The sum total of all these changes and improvements to Akka.Cluster is we were working with, I'd say, about 3 customers that all had kind of a similar problem. They were all running inside Kubernetes, and the problem they had was a huge amount of load would be applied to the system really quickly, either in the form of a deployment or in the form of a horizontal pod autoscaler rapidly starting up new pods. So in one customer's case, they were going from about 10 pods to 80 pods in the span of just a couple seconds. And Akka.Cluster had a very difficult time handling that, mostly because of basically these issues with the gossip and heartbeat systems not being able to keep up with how quickly the cluster was growing. We've since fixed that. That particular user who was affected by that issue weighed in down below on the original problem thread here and let us know that he's able to run 50 node cluster, basically able to scale up to 50 nodes without even changing any of the heartbeat settings or anything like that. So that's a really big improvement. And then on top of that, we also went ahead and decided to attack some performance problems that are directly attributable to Akka.Actor, the sort of core actor module itself. As part of trying to tackle this problem that we thought we had with the clustering system, we decided that maybe some of the mechanisms the cluster uses internally inside Akka core might be at fault. In particular, we took a close look at actor selection, which I looked at it primarily because this is what the cluster daemons use to go ahead and establish contact with each other when we're first forming network associations inside the cluster. We managed to, by just making a couple of simple code changes, improve the throughput of actor selections by about 20% and reduce their memory consumption by 25%. And that was a very simple change that we introduced there that did all that. So that's looking good. We had an n-1 error the entire time inside our mailbox, which meant that if you set your dispatcher throughput to 30, we would only process 29 messages. Whoops. So we fixed that. That's not necessarily going to have that much of an impact on performance for probably most use cases, but in a use case where you set your dispatcher throughput quite low, so for instance, all of the actors running on the internal dispatcher, and this is what runs the actors that do Akka.Persistence, Akka.Remote, Akka.Cluster, all that stuff. Those actors have a dispatcher throughput of 5, so this actually might make quite a big difference there. Your default user actors all have a dispatcher throughput of 30 normally inside Akka.net, so probably not as big of a deal there. But then the channel executor, which I'll go ahead and open up the GitHub issue for that. The channel executor is something interesting that we spent a lot of time working on. I got lots of feedback from Bartosz and from Andrew and some others on how to improve performance here. And originally, the reason why it's called channel executor is we were experimenting with system.threading.channels, which is a relatively new construct that was added to the system.threading namespace as part of I think it came out as part of .NET Core 3, if I'm not mistaken. But it's available all the way back to .NET Standard 2.0, so you can use it, even if you're running on, .NET Framework 4.61 if you want. But we originally were experimenting with that, and here was the big idea. The fork join dispatcher, which is a low-level component that's built into Akka Core, and the fork join dispatcher is basically responsible for running the internal dispatcher and the Akka.Remote dispatcher. So Akka.Persistence, Akka.Cluster, Akka.Remote, all that stuff all runs on top of the channel executor. Or so not the channel executor, the fork join executor. The fork join executor uses a custom thread pool that we implemented probably back when Akka.NET 1.1 was being shipped. And it is a resource hog, to say the least. In particular, where it shows up worst is it's a big resource hog when your system doesn't actually have that much work to do. The reason why is that the system has kind of a very expensive way of waiting for work. So what the fork join dispatcher would do is we would go ahead and let's say we need to have a minimum of 4 threads, or we need to have a minimum of 8 threads for this actor system. It would go ahead and allocate all of those at once. And when that would happen, we would go ahead and have a bunch of threads waiting around for work, which may not ever come. And so as a result of that, we had very high thread counts inside most Akka.NET applications. And this grew by quite a bit once we added the internal dispatcher as part of the Akka.NET 1.4 sort of milestone. We made it so all the system actors all run on their own dispatcher as well. So we thought that we wanted to take a look at trying to make our use of threads inside Akka.NET a lot more efficient than it has been in the past. The easiest way to do that is through a technique that is still very much a hotbed of academic research, and that's known as dynamic thread pool scaling. This means being able to go ahead and on demand, figure out if you need more threads or fewer threads in order to achieve higher throughput and lower CPU utilization. That's basically what it comes down to. That is not something we wanted to try to reinvent the wheel on. The .NET Thread Pool actually does a really good job of being able to manage all those things under the hood. It has access to native APIs that let it measure CPU utilization. It's able to measure how busy or not busy each individual thread is, and they can go ahead and scale that work up and down. On top of that, they have a very interesting data structure called a work stealing queue that allows some more heavily loaded threads to steal work from, it allows very idle threads to steal work from very heavily loaded threads. And that helps reduce the amount of latency it takes between when something gets queued into the thread pool and when it starts. So we decided, okay, in order for us to try to get the best throughput out of Akka.NET, maybe it would make sense if we ran all of our workload on top of the .NET Thread Pool. But this brings us back to the original problem we had in Akka.NET 1.0, which is that some workloads are more time sensitive than others, Akka.Remote being a really good example. In the case of Akka.Remote, we have to be able to guarantee that once a system message makes it into an outbound receive buffer, that has to be delivered within a very short window of time. So if you have a very long work queue in the .NET Thread Pool, that's going to result in a very large amount of latency, and basically it's going to crowd out those time sensitive workloads. So the whole reason we had separate thread pools, in the fork join dispatcher was to provide us with some way of giving each queue of work its own mutually exclusive group of threads. Enter the channel executor. The channel executor is a way of trying to achieve that same sort of discrimination inside our workloads, where one workload has its own queue that is distinct from another workload. And neither workload has the ability to go ahead and monopolize the .NET Thread Pool under the covers. We're able to go ahead and essentially limit the degree of parallelism that all workloads can run at any given time in order to give each of these queues a sort of more fairer chance of being scheduled quickly. That way we can try to preserve some of the real-time nature of systems like Akka.Remote while still being able to dynamically scale our threads up and down. That way we don't use as much CPU, and we might even improve throughput behind the scenes. So our first attempt at doing this was to use system.threading.channels, and I posted the source code for what that looked like down here, where this is basically the core of what actually runs your actors. That's what the dispatching system does. It schedules your actors for execution and then drains the messages from your mailbox each time it runs. Well, this was an executor that used iRunnable, which is the internal construct we have inside Akka.NET for draining a mailbox or running a scheduled task. This is pretty much the same idea as the iThreadPool work item interface that got introduced in .NET Core 3.1, just that we've had this for like 6 years. So we kind of predate some of that stuff. In Akka.NET 1.5 or 2.0, whenever we add support for .NET 6, we're probably going to go ahead and just have iRunnable implement that new interface. That'll help reduce allocations inside our threading system. But the way this works is we create a channel, which is basically just a fancy concurrent queue with a couple of other data structures built into it. And we go ahead and we configure it here. We specify a maximum degree of parallelism. And then every time we try to write a new piece of work to our thread pool, which is one of these iRunnable tasks here, we go ahead and we add it to our channel. And as long as the number of readers is less than the current degree of parallelism, we will go ahead and increment the number of readers. And we will attempt to go ahead and basically use the thread pool to unsafely queue a new user work item. And that'll go ahead and basically execute this method up here, our read channel, which will have us essentially read, and basically keep reading until we run out of items. Basically work items that are sitting inside the system.threading.channels queue. So what's going to happen? And we're going to do this until we run out of items, at which point we'll decrease the number of readers and this thread will get released. So the idea being behind this is that the .NET thread pool down here, whenever it gets items queued into it via our dispatcher, is going to be what decides how many threads it needs to do its job. All of the workloads that are part of Akka.NET, so this includes the default actor dispatcher, the Akka.Remote dispatcher, the internal dispatcher, any other dispatchers we might use for things like Akka.Persistence. We're going to go ahead and run all of them on top of their own channel executor that has its own distinct work queue. But we can limit how many tasks are running inside the .NET thread pool at any given time that are all going to try to read from that queue. That's one of the ways we can go ahead and still preserve this idea of let's say, mutually exclusive workloads without necessarily having to manage our own thread pools. So we tried doing it this way. We also, in the implementation that we actually included inside Akka.NET 149, is we did the same thing but using a task scheduler. Where the code is virtually identical, but the task scheduler allows for inlining of tasks, which means that we can actually reduce context switching to some degree. Now, how often we actually do that, we're not measuring it all at the moment, so I can't really tell you what sort of benefit we get from that. But based on the performance numbers I'm about to show you, it looks like the task scheduler was slightly better, although the numbers between these two figures were pretty much the same. So if I go ahead and I scroll up, we have a whole bunch of figures collected from, and this is another new thing we added as part of this release, our first set of distributed benchmarks. And by distributed, I mean actually running like inside a cluster. That can be, and that cluster can have an arbitrarily large number of nodes participating in the benchmark. So what we did in this case is this is basically a version of our remote ping pong benchmark, which we've been using for a number of years, probably 7 or 8 years. And that's kind of the chief benchmark we've used to try to gauge what's the degree of parallelism what's the throughput that our Akka.Remote messaging system can achieve over a single connection. What's nice about this new benchmark is I can actually measure that throughput horizontally across several connections all at once. So this benchmark starts up. We can go ahead and read the total thread count per node. This is using 1.418, so this is our control. And we're running this entire workload inside Docker Compose because, that's an environment that a lot of our customers and users run Akka.NET inside of. So we want to go ahead and see, what's going on there. And we can see the throughputs we're getting. So we're running across one connection with 5 actors per node, so making for a total of 10 actors. And they're going to they process cumulatively 1 million messages, so 200,000 messages per actor pair. And they're able to do this at about 120,000 messages per second. And this number over here shows us the number of threads in the .NET thread pool and the total number of threads inside the process. So we're running at about 57 threads. These include the I/O threads. They include the threads being managed by .NETty. They also include the threads from our fork join dispatcher running inside of there. Now down here, I have my task scheduler with bounded concurrency, and you can see the numbers inside Docker look pretty similar. The numbers are slightly better for our task scheduler, but not remarkably so. And I think the reason why that is I think the .NET thread pool actually has a harder time. So the .NET thread pool is only running a handful of threads in here. So most of the overhead is coming from, I think, .NETty's thread pool is where most of it's coming from in that environment. Now, if I scroll down, these are our bare metal benchmarks, which are usually more reliable at being able to measure the throughput of what the networking system does. And these numbers that we're seeing for our control, 1.48, are all around about 180,000 messages a second. So it gets, 175, 179, 178 or so, 180, 184, etc. So right around that ballpark. And you can see the thread counts are a lot higher. This is because I think, based on the .NET thread pool scaling algorithm, we're just running with a larger number of threads. But you can kind of see this trend of where it's gradually paring down those threads here. And the lowest thread count we get to is about 68. And this is sort of our control. And this is about what we see with the remote ping pong benchmark even today. Now take a look at what the task scheduler is able to produce. So what's interesting here is, so our initial thread count is already a lot lower out of the gate, but the .NET thread pool is actually doing more work. We have 9 threads versus the 5 and 7 that we're using right here. And our initial numbers are a lot lower than what we see in our control. So we're around 141,000. Bear in mind, all these rounds in this benchmark are all taken from the same 2 actor systems. So the thread pool is having a chance to go ahead and profile our workload and dynamically scale its sort of thread count up and down according to what we're actually doing inside the network. So if I take a look at this, I can go ahead and see that our initial numbers aren't as impressive as, actually the first 2 numbers aren't as impressive as what we get here. But after about the 3rd round, our numbers immediately pick up and they stay up. Now, here's the really amazing part about these benchmark numbers is that the thread pool is actually shrinking quite a bit. We go from 78 threads at the beginning to 51 at the end. And it's because the .NET thread pool is recognizing that a lot of the IO threads and the worker threads that we're using aren't actually necessary right now, and we can do without them. And I think as a function of that, it helps reduce context switching, which should help improve our total throughput and performance. And here's the best part. Our final rounds of this benchmark, so the initial rounds in this benchmark, when I first launch it on my Ryzen computer back at home, it's hitting the CPU to the tune of, let's say, 95%. So it's working pretty hard. At the very end, the fan's not even running. It's down to about 40% CPU utilization. I'm using more CPU right now, keeping 30 Chrome tabs open than I am than I am when I'm running this benchmark right here. And we're still able to get in the neighborhood of 195,000 messages a second, which is better than what we were able to achieve here. And by the way, in this system here, we were still running with a very high degree of CPU utilization for the most part. Now, one important change that's responsible for the improvement in both of these numbers is this method call that we make after the actor system gets created, starting in Akka.NET 1.419. Which is we're telling the .NET thread pool, and there's only one of these per .NET process. We're telling the .NET thread pool that the minimum number of worker threads and the minimum number of IO threads is 0, which means there is no minimum. This allows the .NET thread pool to scale itself down below its sort of normal default values. The default value for the .NET thread pool, the default minimum, is n, where n is the number of threads, is equal to your virtual CPU count. So on this particular computer, you can see my processor count is 16. So I've got 8 cores with hyper-threading. So that's makes for a total of 16 logical CPUs. 16 was the previous minimum for this setting here. And when I set it down to 0, that's what allows the thread pool to drop all the way down to 1 or 2, let's say, worker threads. The total number of IO threads and everything else might be higher. And then in this scenario, I can see that the number of worker threads running on is down to 5. So changing that setting really improved performance quite a bit, and so we've enabled that by default inside the Akka.NET actor system going forward. We might make that configurable. In fact, maybe we should do that even before we release Akka.NET 1.419 today. Although it's very easy to go ahead and override that call yourself. If you want, you can go ahead and basically just call threadpool.setMinThreads again. I don't know what the impact of that call is going to be on every application out there. My guess is what you'll see is a little bit more inconsistency in your initial startup performance. But once your system's operating continually under load, you should start to see basically the numbers really improve because the system, the .NET thread pool is very smart about keeping threads you do need, getting rid of ones you don't. Finally, I had a chance to go ahead and benchmark our system.threading.channels implementation down here. The numbers that we saw were very similar to what appeared inside the task scheduler, but the thread counts and the performance numbers were slightly lower in this scenario here. My current hypothesis is that task inlining is actually simplifying some of the work that's occurring inside of here. And that's also helping reduce context switching, and it's helping improve throughput. And the other reason why we're going to use the task scheduler as our default implementation for this channel executor is it's one less new dependency we have to add to Akka.NET 1.419. So I mentioned, let's see, somewhere in here, this is our code review. Let me scroll back up. I guess I added it to our release notes. I mentioned down here how you can go about turning on this dispatcher inside your application once Akka.NET 1.4.9 ships. This is all you can basically just copy and paste this Hocon into your Akka.conf file or whatever it is that you use to go ahead and configure your Akka.NET applications. This will set up the channel executor in all the places it needs to be in order for you to get these types of benefits. And it's using the safe default values that if we decide to use this by default at some point in the future, this is what will appear in Akka.NET's default configuration is this set of values right here. So I'd encourage everyone to go ahead and try that out. If you're running a performance-sensitive Akka.NET application and you're interested in using this to try to take advantage of the thread pool's tuning behind the scenes, I would go ahead and recommend giving this a try. And then I created a discussion issue in the Akka.NET discussion board right here. Where we're basically looking for feedback from users. I just created this a little while ago, but we're looking for feedback from users who are running this in the real world. We just want to know basically what your configuration looked like. We also want to know what your observed performance before and after were, and then your general degree of satisfaction with the feature. This sort of feedback will help us determine what does and what does not make it into the system defaults in the future. So before I keep going here, Andrew or Gregorius, do either of you have any questions about any of these changes that we made or about the channel executor or anything like that?
No, not really.
Nope. Andrew, how about you?
No, I think I'm good.
Good. Well, Andrew, you're running Akka.NET in a fairly high traffic system. Are you going to give this a try?
Definitely.
Yeah. All right, well that sounds good. I'm going to go ahead and give this a try inside SDK bin ourselves, but we're not exactly running under a server melting workload like some of our customers are. Let's see. Now next, in terms of some of the other stuff on our list, we're going to go ahead and talk a bit about distributed benchmarking and dispatcher performance tuning. We just kind of did that. I'll show the distributed benchmark, I guess, while we're still here. Let me pull this up. Okay, Akka.NET integration tests. So this is a brand new repository. Well, I guess actually it's been around for a little while, but all this code is brand new. These are meant to be integration test scenarios that ideally I think we're going to set this up to run off of Akka.NET's nightly builds. And we want to essentially measure this to make sure that we can do things like deploy a new version of the software into a cluster that's currently running the latest stable version. So we can look for things like wire format breakages. Or in this case, in this scenario, the Akka cluster ping pong code sample that I included, what we want to go ahead and do is measure, is there a performance degradation that we can observe inside a real world environment, like Docker or Kubernetes, for instance. So this benchmark that we created here can be deployed via Docker Compose or via Kubernetes. I kind of documented how to do both down here. And if we take a look at the main README, we have some instructions on how to do things like build Docker images using custom NuGet feeds. So for instance, when I was testing these dispatcher changes, I went ahead and added a new package source down here that referenced a local folder where I copy NuGet packages and make locally. And I was able to go ahead and use that to help rapidly test new versions of Akka.NET to go ahead and see what sort of performance changes I could expect. So this is something that I kind of worked on in order to help support some of the changes we were making in Akka.NET 1.4.9. That's available now. That's all open source under Apache 2, if anyone wants to take that for a spin. Next thing I wanted to discuss is Akka.Persistence.Sql batching changes. Let me go ahead and pull that issue up on screen real fast. So I guess both Gregorius and Andrew, I expect both you guys have some input on this section here. Let me go ahead and pull this up. All right, Gregorius, would you mind? I'm just going to get this issue up real fast. Would you mind walking through what the problem was here and how we're trying to fix it?
Well, previously, the way batching works is that um, every request that came through will be put inside a queue, and then the journal batching will actually take a chunk of that and execute it inside a transaction, basically. Uh, what it does really good is it preserves ordering. So all of the requests inside the queue are processed as it is when it is received. The ordering is preserved. The problem is that if you do that, you can actually have a read and a write happening at the same time, even a read, a write, and a delete inside the same transaction. So
All covering the
that's
same part of the index, right?
um, not necessarily.
But that was the case we were looking at, where you're reading, writing, deleting all the same data potentially inside a single
Well, yeah,
transaction. Yeah. Yep.
yeah. So yeah, that's a big no-no. So we tried to fix that. Um, right now, the code that I'm writing right now is it's not as consistent in ordering. It's uh, approximately first in, first out. It looks at two different queues basically, a write queue and a read queue, and whoever and it looks at the first item in both of those queues and see whoever who's actually came in first, and then it batches the actual request inside that queue.
So we're
If that
batching
makes any sense.
so we're batching reads and writes separately from each other now. Um,
Yes,
so
and
multiple reads can all be grouped into the same transaction, but they can't be grouped in with writes anymore.
hmm and then for the case of writing, write kind of operations, it is you cannot have both a write and a delete in the same batch. If the queue starts with a delete and it encounters a write, it will stop there. If it starts with a write and it encounters a delete, it will stop there. So it only batches one type of write operation at a time.
Got it. That makes sense. And so I think the plan, it sounds like, is we're going to go ahead and push this into Akka.NET 1420. Um, and I think we're going to mark the version of Akka.Persistence we shipped then as pre-release. Is that right?
Hmm.
Yeah. And
It
that's
should
because
be.
that's because this actually changes the behavior of the batching SQL journal, which we know we have people using in production. This actually changes the behavior pretty significantly. We are trying to make it safer. um, and I think you had a very insightful comment, Gregorius, which is you said that this journal is very good at passing benchmarks, but probably has some significant problems handling real world workloads. Um,
Yeah.
and I agree with that. As Andrew and I were discussing in Gitter earlier today, uh, having something be functionally correct is the first requirement before we can go and make it fast, right? So
Hmm.
I think this is probably a good case here. Andrew, do you have any comments on this before we move on to talking a bit about Hyperion?
Not specific to this topic, no. Aside from Gregorius did an amazing job trying to fix a lot of the architectural concerns that were in that journal.
Yeah, well, I agree with that, and I'm looking forward to getting some feedback from users once we ship this in 1420. Now, I think the next things that we had on our list here, we're going to talk a bit more about Link to DB in a moment. But I wanted to talk a bit about the Hyperion changes that we introduced in Akka.NET 1.4.19. So if I recall that, I actually got to go pull up the Hyperion repository real fast. I believe the big thing that you worked on there, Gregorius, this was all about trying to stabilize cross-platform wire formats. And funnily enough, we
Hmm.
just had a bug report about this maybe an hour before this call started. Um, so so yeah, do you want to talk through sort of what we're trying to do? I guess it's really Hyperion 0.10 is the one we want to really talk about. That's where the
Hmm.
big changes are. It looks like my version tag is missing there. So let me go ahead, go back to Hyperion, go back to releases. Here we go. Oh, it's 10.0. That's my bad. Okay. Okay, there we go. So generic cross-platform serialization. So go ahead and take that away.
Um, the idea is, before this change, we actually have to introduce all of the differences between .NET Framework and .NET Core. Uh, the main problem being the difference in DLL names. Where in .NET Framework it is called MS Core Lib, and in .NET Core is I forgot private that something, but
So yeah, for users who haven't dealt with this before, between .NET, Core, basically .NET Framework 4.8 and .NET Core 1.0, Microsoft changed the default namespace for all primitives. So integer, string, long, all that stuff is in a totally different namespace than it was before. So trying to do serialization where you have, let's say, a .NET Core application talking to a .NET Framework application, and you're trying to use polymorphic serialization, which is what both Hyperion and JSON.NET are doing in Akka.NET. That actually is not very easy to achieve right now because of that. We have to essentially add a translation layer to go ahead and convert the new type names back into the old ones and the old ones back into the new ones, depending on which platform you're running on. So this is a problem that, although it sounds on the surface like something that's going to go away eventually, the truth is that it's going to take a lot of Akka.NET users a long time. If they're, let's say, a big enterprise business working in finance or healthcare or government or something like that, it's going to take them a long time to kind of move everything off of .NET Framework and onto .NET Core, because organizations like that tend to be very conservative with how they take risks on adopting platforms. And as a result of that, we're probably going to be dealing with these types of problems, uh, for a long time. And they're actually going to become more common, not less common, as more and more of those companies actually start getting on board with trying to move from one version of the framework to another. This sort of stuff's going to come up where they're going to have one set of services that are being migrated to .NET Core, bunch of services that are still running on .NET Framework. So this is kind of the crux of the big changes that we introduced. Gregorius, I believe you added a setup class for being able to go ahead and specify these Lambda functions that allow you to go ahead and convert from one package name to another. That's right,
mm-hmm.
and that's how we decided to address this. Right, was make it so you could just add a bunch of little functions that'll say convert from the system.drawing.primitives namespace to just system.drawing. Since they moved some of those color types and everything around in .NET Core,
Mm-hmm.
yeah.
Mm-hmm.
So we have a new setup type that I believe you actually documented this. I think if I go to the Akka.NET website and we take a look at the Hyperion docs, I think you actually show how to use this in a code sample up there. Whoops, that's not how you spell Hyperion. Yeah, if I go to, let's see, serialization, how to set up cross-platform serialization compatibility in Hyperion. Yeah, here we go. So we actually walk through how to cover some of this inside this section here. In fact, that reminds me, I'm going to need to go ahead and update our release notes and include this, because this kind of merits its own call out, I think. So that's what's going on with Hyperion in this particular release and how we're integrating it into Akka.NET serialization system. Now, as part of the 1.420 release, we talked a little bit about some of the things that are coming there. I would say the big changes that are coming is the batching SQL journal, which we just discussed. We're going to finally remove a whole bunch of old crap that we had as part of the Akka.NET 1.3 rollout for adding cross-platform support between .NET Framework and .NET Core. So we're going to go ahead and replace that inside 1.420. We're just going to get rid of a lot of those if-def statements and compilation directives. And then we're also planning on doing a significant amount of performance fixes to Akka.distributed data. Akka.cluster sharding runs on top of DData. And so these performance fixes that go into that library will also improve the rate at which shards are distributed, the rate at which things are rebalanced, and so forth. So there'll be a lot of ancillary benefits to sharding, in addition to any benefits that end users who are using DData directly will receive. Now next, we've got to talk a little bit about the Akka.Persistence.Sql Roadmap. So the first question, actually, I guess I'll kind of couple these two questions together. And Andrew, I guess we'll start with you. There's been some discussion about just deprecating the batching SQL journal outright. It seems like kind of a hacky idea that's probably lived past its useful lifespan. And having a high performance journal that's able to maintain atomicity is probably a better approach going down the road. And that's what you've tried to do with your link to DB implementation. So what are your thoughts on that?
I personally think that it's worth looking into. The big thing about the link to DB journal is it is based on the Akka.Persistence JDBC project on the Scala side of things. So it is a proven and sound architecture from that platform. We're able to use link to DB because on that side they use what's called SlickDB, which is like actually a reactive streams compliant database provider. Like it runs on a materializer and everything,
Oh
or it
wow.
can if you choose to. Yeah, we don't really have that, but link to DB gives us a lot of really good functionality as far as letting us define the queries that would be needed to operate on a SQL-based journal without having to do a lot of provider-specific code. And it also has some really good multi-insert functionality built in, so that gives us really good scaling performance as things buffer up. We've been using the journal and snapshot in question at my organization for a little while now, and it's been working very well. There is one very minor edge case. If you're persisting multiple events at once and you need atomic write on that I'm going to fix this weekend, it's a very, very, very edgy case, but it's going to get fixed. It's going to turn down the performance numbers on some of the scenarios by up to 20% for some of the scaling out writes. But it still winds up being far faster than the batching journal for those scenarios. And I'm willing to bet that with the changes in the pre-release of the existing batching journal, it's going to be fairly in line with those numbers for single write scenarios.
And then Gregorius, what's your take on retiring the batching SQL journal and just moving forward with, let's say, the link to DB approach for that?
Totally agree.
Yeah.
Because the problem is that with the current batching journal, there's really no way of guaranteeing the ordering.
Yeah. I think that's a problem. I think the mixing reads and writes over the same index within the same transaction is pretty risky. I don't think many DBAs would be thrilled with that. But yeah, I also think that the batching SQL journal was something that was always more of an experiment, and we probably should have been more critical of it earlier before we released it to end users. So lesson learned there. I think link to DB sounds like the way to go. Andrew, once you get that bug fixed, do you think this thing's basically ready for us to start going and really, I guess, promoting it more frequently?
I would think so. I'm still hoping to hear for any feedback from people using the persistence query parts of that. That's the one functionality that we don't really use at our org.
Got it. Well, hopefully we can get some users. In fact, what I recommend doing is we should go ahead and create create a little discussion issue, just like how I did for the channel executor, and see if we can draw some people's attention to it that way. And try to get some feedback from people who are very heavy Akka.Persistence.Sql users. We know they're out there, so we just got to get them to try it out and maybe hold their hand a little bit for just the process of switching from one implementation to another. All right, last I want to go ahead and finish up with a couple community updates. So first, since our last meeting, I've gone and published paired YouTube videos and a blog post. So I wrote a little blog post on how to build headless Akka.NET services with iHosted service. Most of our code samples were still referencing things like Windows services, which, while useful, are now represent a relatively small corner of the .NET ecosystem. What a lot of people were asking about is how to put together an iHosted service inside something like a headless Kubernetes application. So I kind of walked through the formula for how to do that in there. If I pull up the Akka.NET integration tests, and you take a look at, if I take a look at my little cluster ping pong sample here, all right, let me look at the source code, GitHub. All right, there we go. I go and pull this up and take a look at the Akka service. And we grab this. This is pretty much how you do it right here. The one thing I forgot to do in the video is you need to go ahead and grab a reference to the iHost application lifetime via your dependency injection provider. And then at the very end, you go ahead and add a register and remember removed hook, where you go ahead and tell the lifetime to stop the application. That'll go ahead and make it so if your node gets kicked out of the cluster, the process gets destroyed afterwards. That way you don't end up with a bunch of zombie processes that aren't doing anything hanging around inside Kubernetes. The other way you could go ahead and kind of accomplish the same thing is if you're using Kubernetes to put a liveness probe on top of the Akka.NET remote port, that liveness probe will fail after this node gets kicked out of the cluster because the actor system will shut down. And that'll cause Kubernetes to go ahead and kill this process too. But the right way to do it is to really grab a hold of this high host application lifetime and call shutdown application stop application once you get removed from the cluster. That'll make sure you don't get a zombie process either. And then finally, if I go back here, I added a YouTube video, which I'm going to pair with a blog post. I also added a YouTube video on best practices for integrating Akka.NET and ASP.NET Core. And this is all about how you can go ahead and basically introduce Akka.NET as an iHosted service inside a running ASP.NET application, and how you can go ahead and expose Akka.NET's functionality inside, SignalR hubs or MVC routes and controllers, that type of thing. And so I think both these videos are maybe, 5 to 10 minutes long each. So they're pretty short. I definitely recommend you take a look at those if you're interested in using Akka.NET with .NET Core. Hopefully we'll be doing a new blog post on the Akka.NET and ASP.NET stuff pretty soon. I'm also getting ready to put together a full-fledged demo showing how to integrate Akka.NET and Kafka together. So that should be useful as well. And that'll come live with a code sample to boot. All right. Well, gentlemen, is there any other business that we should discuss as part of this month's meeting?
No, not really.
Nope. Andrew, do you have anything?
Nope, I think I'm good.
All right. Well, in that case, meeting adjourned. I'll see you all in GitHub and in Gitter. And thanks again for your participation this month. Really appreciate it. I'm really excited about the 1.49 release. Hope all of you guys get a chance to go ahead and try it out as soon as it's on NuGet today. I think you'll see some pretty dramatic performance improvements and a much smoother experience running Akka.cluster. So thanks again for your time. Really appreciate it. And we'll see you on Gitter and GitHub. Take care.